Hello students, welcome to Exam List. So in this part of the lecture I'll talk about fields. Okay, why do I call fields? So consider you have this liquid moving through and each point of the liquid here, so consider this is a molecule of the liquid, then the motion of this liquid molecule will have a particular path. Say this is the path. Similarly, if I have other molecules here, then each of this molecule, they have their individual path, and the whole path or the combination of path of all other molecules, they decide the final path of the fluid. Now something interesting happens if I say that this fluid has a density which is not constant. So rho is not constant, and if I say that density is a function of x, y and z, it means that density can be considered as a field variable. By field variable, it means you take some variable and you evaluate it at a particular space point or space-time point, or you can say at a particular location. So here you can see that rho at this particular point is going to be different. Rho at this particular point of the fluid is going to be different, and rho at this particular point is going to be different, because we are talking about a fluid whose density is a function of space point. That is, if you want to find the density of a fluid, you have to take a small sample of the fluid at this particular position and you calculate the density. You will find the density found here is different from the density found here, and it is different from the density of the fluid found at this particular point. Okay, so what do you understand from this? You understand that density is a function of x, y and z. Also, there is one more thing. If this is true, then velocity is also going to be a function of x, y and z. Now what do you mean by velocity as a function of x, y, z? This is I call as the velocity field. You see, the motion of the fluid is such that the velocity can be defined at each particular point. So I can define a velocity at this particular point. Okay, velocity is, say, v of x, y and z. If I go a little further, you see that the velocity direction has changed. The velocity is now in this direction. So velocity here I am writing it as vx dash, which is calculated as x dash, y dash, z dash. So what do you understand from here? You understand that this velocity v is the field velocity. Okay, or I can call it as the velocity v is the velocity of velocity field, or I can call this that the motion of the fluid can be also described by using field variables. One is density, which is a function of x, y and z, and another field variable is velocity, which is a function of x, y and z. If the velocity of the fluid and the density of the fluid changes with time, then at each point in space and at a particular time we can define a density. So now density will become a function of time and x and y and z if the density not only changes with space point but also time. And because of this case, the velocity or the velocity field will also become a function of time as well as the space-time points. So instead of working with velocity v of each particular molecule, I am working with some kind of velocity distribution that defines the fluid. This is the idea behind continuum mechanics. Okay, this is just like an introduction to continuum mechanics, where instead of looking at the motion of each microscopic particle, you look at the rate of change of these field variables that can be defined at each point on this continuous fluid. This is the idea of field, and this is how field variables are introduced in the fluid mechanics, because fluid mechanics is a part of continuum mechanics. So this particular v here represents the velocity distribution with respect to space. Why is that? Let me remind you that when we were calculating delta m, okay, I didn't tell you v is the velocity of the fluid. I tell you what? I said at this point the velocity of the fluid be x, and at this point the velocity of the fluid is going to be different. V of x is going to be del v of x plus del v of x divided by del x into delta x. So here I am actually working with velocity field. Velocity field means distribution of velocity of fluid at different positions. This was only the example of velocity field of the fluid for x direction. We have similar expression for y and z direction. Okay, and using these variables, which I call as velocity field, I define this continuity equation. Okay, so can I go from here to here? Interesting, right? Because equation number 2, let me call it equation number 2. So equation number 2 was continuity equation when the density was not constant, and equation number 1 is the continuity equation when the density of the fluid was constant. So let's try to understand if we can go from one to the other. Okay, what happens in this case? In this case, the density rho is not a function of time because density is not changing with time. So d rho by dt for incompressible case is going to be 0. So if d rho by dt is going to be 0, then minus del dot rho v is also going to be 0. Okay, then what happens if this is 0? This can be written as rho into del dot v plus v into del dot rho. Okay, and now this is 0. First of all, understand that gradient of rho is also 0 and gradient of v is also 0. Gradient of rho is 0 is a direct consequence of this fact that rho is assumed to be constant in space as well as time. So since it is constant in time, so d rho by dt is 0, and for an incompressible fluid we cannot expect that rho is changing because the definition of incompressible fluid is that rho is independent of space points. So del dot rho is going to be 0. So the only thing that remains is del dot v is 0, because see, the left hand side can be 0 if this term is 0 and this term is also 0. Now this del dot v is equals to 0 is directly connected to this thing a1 v1 is equals to a2 v2. So take it as a homework and solve it yourself. Let me give you a hint. See if you can use Stokes theorem or Gauss divergence theorem and go from del dot v equals to 0 for incompressible fluid and prove that this equation is equivalent to saying a1 v1 is equals to a2 v2. Okay, so what do we understand? We understood that point number 1, for an incompressible fluid, equation of continuity says a1 v1 is equals to a2 v2. Okay, this is the first point. Second point, for an incompressible fluid, the general continuity equation number 2 drops down to a simple expression which is d rho by dt equals to 0 and del dot rho v is also 0. From this we get an important point which is del dot v is 0, and this expression del dot v is 0, which is obtained when in equation 2 we apply the special case for incompressible fluid, this is directly related to first one, that is a1 v1 is equals to a2 v2. Okay, so this is the conclusion. So what do we learn? We learned how to deal with continuity equation, we looked at general form of continuity equation, and we learned about this rho being a field variable and velocity being a field variable that we are actually using. So in the next lecture I'll discuss more on this field variable so that you get a complete picture of what's going on.